The content for today will be dealing with modeling of the hydration process and the temperature distribution in young concrete material. Let me introduce myself. My name is Jiří Rimeš. I work in Červeňka Consulting, mainly on material models and characterization of micromechanical problems. And also I'm dealing with the transport problems, so that's why I will be in charge of the meeting today. As you know, probably most of you already know ATENA. You know that we are dedicated to modeling realistic concrete behavior. In the software, it's possible to model concrete under cracking of concrete under tensile stresses, or even crushing concrete when it's subjected to significant compression stresses. Also, similar things is possible to model for the reinforcement, where we can model the yielding of reinforcement and even eventual rupture of the reinforcement bars in the concrete. And this all can be used for modeling of static, cyclic, earthquake loads. And for today, we will be focusing on the content which is shown in this bottom right corner of your screen, which shows the fresh concrete hydrating and development of the temperature inside of massive concrete elements. Before we get to the core of the today's meeting, I would like to bring your attention to our new ATENA, the version 5.9.1, which is now available for download from our website. It has some improvements since the last version. One of the most important features is that it's possible now to apply for trial licenses, so you can test ATENA for 1 month for free, and you will have all the capabilities of the software. It's not a demo. It's not limited by the amount of elements or by the amount of nodes. It's a standard version for your evaluation. You can apply for the trial license when you install ATENA. You download it from our website, you install it, and then open ATENA Center, and you can. And there is some tab called, I think, ATENA license or your license, and through that you can apply for the trial version. Also, in the new ATENA model, there are some improvements regarding the agent modeling. Mainly the new creep models according to two new standards. Also, it's possible now to model some deterioration mechanism for reinforcement bond properties, and also we are continuously trying to improve our support for concrete 3D printing. So yeah, if you want to try the new version, please go to our website and download it there. So now back to the content for today. So as I mentioned, we will be dealing with fresh concrete and the heat it releases during its hydration. So I will start with briefly discussing how to preprocess such a problem using the preprocessor for ATENA Science, which is the GID software. We will be today focusing in the transport module. Many of you probably are most familiar with the static module, which is normally used for evaluating the static loads on your concrete. But today we will be using the transport module. I will be talking about how to set the transport properties, how to define the properties for your concrete mixture, how to set the hydration characteristics based on the given cement type, also how to apply appropriate initial and boundary conditions for the problem, and then I will move to some to post-processing the results in ATENA Studio. At the end, I would like to show some example of the application from our consultation practice, and hopefully there will be some remaining time for the discussion and for Q&A. So let's get started with some motivation why we are even interested in such problems. This is some general concrete knowledge, so please be patient if it's too basic for you. So as we all know, that when the concrete hardens, it's due to the cement hydration, which is a chemical process where when the cement base becomes solid, and it's a chemical reaction. It's an exothermic process, so the heat is released during the process. And as the cement base hardens, many components of the hardened cement paste are formed. Mainly the calcium silicate hydrate and portlandite, but also some others. One of them is ATENA. This is the mineral in a kind of needle shape, which have one which is kind of problematic at high temperatures, because above approximately 65 degrees C, this mineral becomes unstable and cannot be formed. And if the temperature in the fresh concrete exceeds this value, the mineral is not formed. However, all the components which are needed for its formation are still there, still presented in the concrete or in the cement matrix. So then later on, when the temperature decreases due to the cooling, in time frame of weeks, months, or even years, this ATENA starts to form, and in the cement paste, as can be seen on this picture, it causes expansive stress in the matrix, and the result, this is the view of the microstructure from backscatter electron microscope. You can see the ATENA forms in here and on the boundary of the aggregates. And this expansion finally results in cracks in the macroscopic or even structural level, as can be seen on this picture, which shows cracks in the sleeper, in the railway sleeper. Another problem with the temperature in fresh concrete is, even when it's less than 65 or 70 degrees C, is that there can be a gradient of the temperature throughout the structure. This gradient means that the thermal expansion at different position of the element or the structure will vary, which will cause differential thermal cracking due to the gradient, because the element, if it's massive element, it's internally restrained, and this leads to the crack formation. This can be seen, in this impressive photo of the dam in the United States, where the cracks are even visible from this kind of aerial view. So this is the motivation why we need to focus on the properties of the fresh concrete, and why we need to analyze it mainly when casting massive concrete elements on structures. So in ATENA and in the GAD preprocessor, we have implemented a model which can get the characteristics of the young concrete, and it can get these characteristics, and it updates this characteristic throughout the hydration of the material. So in the material definition, in the transport module, you can select this young concrete material, and for this young concrete material, we use the ferrite module. This module based on the representative element volume, meaning that in this representative element volume we have different components of the concrete matrix, and based on their volumetric amount, we upscale the properties and get the macroscopic characterization of the concrete. The definition, meaning the inputs for this circuit model, can be either defined by the user directly, or we have another tool which can automatically generate them, which is called Conmix. This Conmix app is even available when you open ATENA Center. You can directly run it, and it can give you some useful characteristics of the concrete of your concrete mixture, which you can use either then in ATENA or separately for your for other purposes. So how to run the Conmix when in GID, when you go to the material definition, select the young concrete, then in the basic tab you have this, and when you select the checkbox activate concrete model circuit, you have another checkbox appears, which states run Conmix for circuit. If you select this and update the window, the Conmix tool shows up. It's a tool for where you can input components of your concrete mixture, and based on that, as I mentioned, the overall parameters are computed. There are several, not several, actually 5 tabs in this app, which I will present in the following slides. The first tab, which is very important, specifies the unit for the output of the Conmix. This should be treated with great attention, because the units set here must be the same as those defined for the ATENA for the ATENA kernel. I mean, in GID you have the option to choose the problem units for your problem, and the units in Conmix must be the same. Otherwise, the output from Conmix, which is later used for the calculation, will have different units, and the result will make no sense. So I suggest that every time you open Conmix, you check that these units are correct, and compare them with the units which you set in the GID preprocessor. Another tab in Conmix specifies the mixture proportions. The mixture proportions specified in here gives the proportion per unit volume of your concrete. So in here, it's the user should input the amount of cement, the amount of water, the amount of aggregate, and potentially the amount of supplementary cementitious material per 1 cubic meter of the given concrete. There are some predefined compositions for typical concretes based on the European standards. So for those of you who are not familiar with this standard, there is this drop-down list where you can select the type of concrete. The seams is basically abbreviation for concrete, and then you have 2 numbers. The first one specifies the characteristic cylindrical, and the second number characteristical cubic strength of concrete. So if you select these, there are some predefined compositions, some typical concretes, which can be used as the first approximation of the property. So you can, if you know your concrete composition, you can directly input it. In the next step, the next step is dedicated to the specifics of the hydration process, of the how the degree of hydration increases in time. Basically, there is inputted some predefined function which is based on the affinity model published by Kevin and Passavento in 2006, and it calculates the rate of hydration. This is the rate of the hydration in time based on this kind of equation, which uses three model parameters and gives this kind of shape. This is a reference hydration curve, which is assumed at constant temperature of 25 degrees C. And then during the calculation, if the temperature is increased, the rate of hydration is automatically accelerated using the Arrhenius law. The Arrhenius law, it's a basic principle from chemistry, and it relies on the activation energy for the cement clinker, and if the temperature is increased, the rate of hydration is accelerated, and if the temperature is lower than the reference 25 degrees C, the rate of hydration is slower than the reference one. Again, there are some predefined parameters of this model for typical concretes and for typical cements. Mainly is for the basic Portland cement, or according to European standard, we call it CEM1, which is basically rich light cement. Or again, you can define the properties for your own, either based on your laboratory experiment or some literature data. So one parameter is for this model is the curve, and then there is this activation energy parameter, which scales the rate of hydration based on temperature, and the final parameter is the potential heat, which specifies the amount of heat released by the hydration of 1 kilogram of cement clinker. The more details about the composition of the predefined typical cements and typical concretes can be found in ATENA theory manual, where you can find these tables, and you can see what is the composition of the different cements used in this Conmix tool, and based on that you can probably find the closest match which corresponds to your cement, and then start your modeling with these values. If you don't want to rely on this Conmix tool, you can input all these parameters manually using the directly from GID. Now I would like to give a little comment on this hydration mechanism, because you actually have three different possibilities how to input them manually. If you in GID, if you choose the option table, it means that you will input the relationship between the time and degree of hydration based on your actual measurement, and it will not be scaled up based on temperature. So this already includes the effect of potential increased or decreased temperature, or some retardation of the hydration due to the decreasing relative humidity, etc. Then you can enter the reference curve for the hydration based on as a table. So if you don't want to rely on the model on the affinity model which I showed earlier, you can directly input the data based on your laboratory measurement as a relationship for time between the time and degree of hydration. And finally, you have this option to use the analytical model, where you again input the three parameters of the model. So this is concerning the semen hydration, and final option, which is used for getting the overall characteristics of the or get the macroscopic characteristics of the concrete, is this table, this tab called params, which specifies the thermal conductivity and specific heat capacity of each component of the mixture. Again, you can generate these automatically for the given aggregate in the mixture, and for the chosen supplementary cementitious materials, and basically for the cement, this is a constant, as well as for water. Last parameters specified here are these two. One defines the water content in the concrete at 80% of relative humidity, which is and this value is later used to fit the absorption isotherm of the concrete. And the last one is water absorption coefficient, which is used to reduce the diffusivity of the concrete. Finally, the Conmix tool generates two files, which can be viewed in the Notepad or some other text editor. One summarizes all the inputs which are later copied. When you execute the calculation, these inputs are copied to the input file for the calculation, and a second text file gives the relationship between the time and the degree of hydration for the chosen cement paste. These files are stored in your ATENA calculation folder, which is at the same location as the GID model. So this is concerning the definition and the definition of the material. I'm not sure if there are any questions to this content. Let me see the chat box. Okay, now I managed to find the chat box. So no questions so far. So let's continue with the definition of the problem, meaning mainly the initial and boundary conditions. There are two types of initial condition which needs to be specified for the concrete. One is the temperature, and one is the initial relative humidity. This this means that that when executing the calculation, this is the the value of the humidity and temperature from which we start to calculate the development of these properties in time. These are again part of the of the material definition. They are not placed in the section with the boundary condition, but they are part of the material definition. It can be specified that this parameter is not constant over the volume of your concrete, but it can be a function of the global coordinate. And another feature which I would like to discuss here is that these properties, I mean, during the analysis, we can either focus on temperature or for the moisture transport or for both of them. And if we want to exclude one of these from the analysis, this can be done in the interval data settings. For instance, if we are only interested in the thermotransport, we can use this option, fixed moisture degree of freedom, which technically means that the relative humidity in the material is kept constant and only the temperature is calculated. Then we can specify the boundary conditions. There are two basic type of boundary conditions. Either it's a Dirichlet boundary condition, and then it's the Neumann boundary conditions. The Dirichlet boundary conditions, I would like to a little bit stress this feature because it's kind of specific in ATENA, because as you know, most of the boundary conditions in ATENA are defined in incremental form. For example, also applying the static flows, it's always incremental. So similar to this, also the Dirichlet temperature in the transport analysis is in the incremental form. What it means is that if you specify the Dirichlet temperature 10 degrees C in one interval, during this interval the temperature will be increased by this 10 degrees C. It does not mean that you fix the temperature at 10 degrees C, but if you start with 20 degrees C and prescribe this 10 degrees C difference, at the end you will end up with 30 degrees of Celsius. Similarly, this is for the humidity. For the Neumann boundary condition, it's easier because you directly prescribe the thermal or the moisture flux at the given position. Those are the two basic boundary condition, and then we have one kind of combined boundary condition for temperature and moisture transport. Generally, I recommend to use this condition if you want to simulate the flux through the boundary. At the beginning, you specify the external temperature and the external humidity, and then you define the transport parameters at the boundary. For the heat convention and radiation, you define the heat convention coefficient and the emissivity of the surface, and for the moisture convection, I suggest to use this option when you define the moisture convection factor.
Also, there is one option to use this sandstone calculation, which uses the which uses the model which is suitable for fresh concrete, and it calculates the moisture evaporation from the fresh concrete based on the data from this sandstone company. In this convection parameter, you can include the impact of for example, some additional isolation on the concrete. For example, if the concrete is placed to a formwork, which then provides some thermal insulation, you can include this insulation in this parameter. Basically, it's the inverse value of the sum of resistant insulation factors for all those layers which are at the boundary of the concrete. So now I would like to show some example for such an analysis. But maybe before we get there, there are two questions. So let me. So one question asks, do you have the ability to factor in insulating the concrete from perimeter? Okay, so if I understand correctly, this is dealing with the option how to model the isolation layer. So it can be done either in this way, as I explained, or it can be, or you can actually directly simulate the formwork in the transport module. When you if you create another like a thick layer of material, you can directly assign the isolation properties to this layer. I'm not sure if this is. I hope this was where the question was aiming. Another question is, in Conmix, is it possible to use and define the specific time of the hydration in a certain period that corresponds directly to the degree of hydration? Or we would need to use the relationship between the time and hydration as shown in the figure to get the result. This is question from Asdam, and I think this can be done if you use the. Let me go back. So if you don't use Conmix but you input the relationship for the degree of hydration manually, it can be given directly as a function of time and degree of hydration. So in that case, you can directly specify that for example, at the age of 1 day, the degree of hydration is, I don't know, let's say 20% or 15%, and then at the time of 14 days, the degree of hydration is 85%, etc. So I think this is the way how to do it, and in that case, the rate of hydration will not be scaled based on the external temperature or based on the relative humidity. So I hope this answer the question. So if there are not further questions at this moment, I would like to proceed to the example of application of this model. So let me consider this example. This consists of some existing concrete foundation, here indicated by the yellow color, and on top of this old concrete, there will be placed new fresh concrete, forming this abutment for the bridge. Then from this side, it will retain some ground pressure, and the bridge will be on top of this massive foundation. The maximum thickness of this new element is 2.3 meters in this direction. It is assumed that it will be cast in winter. The analysis will span from 0 to 28 days of the concrete. And actually, for this analysis, we will neglect the effect of self-acidification because the water to cement ratio is quite high, and we will assume sealed curing, so there will be no moisture evaporation to the surroundings. Our goal will be to get the maximum temperature inside of this element, and also to evaluate the gradient throughout the structure, and also compare between different cement types and different options for thermal insulation of the fresh concrete. So basically, this summarizes the initial and boundary condition. The external temperature at this season was assumed from the long-term data as 0.2 degrees C, and this temperature was also used as the initial temperature for the old concrete at the bottom. And since this concrete is in contact with the ground, we assume that the cooling of this surface is very efficient, and it can be assumed that the temperature is kept constant there. Therefore, we can prescribe the fixed direct boundary condition on the bottom surface of the foundation with the gradient of 0 degrees C. Then on the top surface and on the side surfaces, we assume that there is some flux through the surrounding environment, to the external environment, which is governed by the difference between the temperature of the concrete and the external environment, and the heat transfer coefficient. This heat transfer coefficient was calculated as the inverse value of the thermal insulation factor, which based on the standard, because this is actually based on the Czech standard, which specifies this factor as 0.04 meter squared Kelvin divided by watt. So this specifies the condition for the old concrete foundation, and for the newly placed concrete, we include to this heat transfer coefficient also the impact of the potential insulation, which in this case is only calculated as the based on the thickness, based on the 2 centimeters of the wooden layer of the formwork, and it's and the heat or the thermal coefficient of the of this wooden layer. The initial temperature for the fresh concrete was assumed as 5 degrees C based on the assumption from the cement provided by the cement by the concrete provider. Maybe before I show the results, I would like to show this model in the GID preprocessor to give you more idea about this simulation. So this is the model. It's composed when I display the materials in the model. It can be done by draw or materials. Oh, sorry for the check names here. One name is one material is on the bottom and another material is on the top. We can further check these materials when we open the material definition, and we see these materials in here. So for the bottom part, we use the material prototype concrete, and for this concrete we use, and the type of analysis is temperature, because we are not in this case interested in the moisture diffusion. We only want to know the temperature distribution. So this is the definition at the beginning, and based on that we just need to define actually 3 parameters for the on concrete. One we call this is the thermal diffusion factor. In here it's labeled K1010. And another one is the specific heat capacity. So those are the typical values for concrete, for the hardened concrete. Then we specify the initial temperature. As I mentioned, it's about 0.2 degrees C, because we assume that the casting is done in winter. Then we have this another material, which is called, which is specified in here. And as you can see, for this material, we use different material prototype. It's not concrete, but it's young concrete, which use this Sahit tool to get the properties of the material. And in here, in each step, we fill out the properties needed for characterization of the concrete mixture. Here we specify the density and the mass of each phase per 1 cubic meter of concrete. Here we specify the specific heat capacities. For example, for this problem, we use we defined the hydration curve as the reference one at 25 degrees C. So we did not use the Conmix, but we directly input the data. And here we specify the initial temperature. Because, as I mentioned, we are only interested, we assume sealed curing, and we are only interested in getting the temperature values in the interval settings. We use this option specifying to keep constant the relative humidity during the analysis, and all this analysis is combined is done in 2 intervals. Once with a little bit final step from time 0 to 7 days, and then in a second interval little bit coarser time step from 7 to 28 days. When it comes to the boundary condition, I will quickly show them that we can in the first interval we use this fixed condition at the bottom, and then for the surfaces of the concrete, we use this combined moisture temperature boundary for surface, which differs at the bottom and at the top of the structure, because at the bottom there is assumed no formwork, and on the top there is this additional insulation provided by the layer of formwork. So when we look at the data, the results are shown on this slide. On the left, you can see the development of the temperature over the time. As the hydration starts, the temperature starts to increase, and after some time, when we reach the peak, then the element gradually cools down. And on this slide in here, you can see the development of the degree of hydration in time. So we can see that the highest degree of hydration is reached in the center, and on the surfaces where there is little bit lower temperature, the hydration is slowed down, and the ultimate degree of hydration after 28 days is lower than compared to the center. On the bottom of the structure, we don't see any data, because this is assumed as some existing concrete foundation. We can, if we make a cut through the position with the highest temperature, we can get the gradient of the temperature throughout the thickness. In here, we try to compare the impact of different external temperature. So the reference one is in here at about 0 degrees C. We see that the difference between the outer surface and the center is about 34 degrees C, and the maximum temperature would be something like 55 degrees C. In case that the external temperature would be kept to, let's say, a little bit extreme value, it would be very hot summer, 40 degrees C. We already exceed 70 degrees C in the center, and the gradient between the center and the surface would be about would be a little bit less than 20 degrees C. In here, this is a comparison of some, in case that we use some additional insulation of the surface. In here we assume 20 millimeters of the insulation, and the external temperature is kept the same. And we can see that this additional isolation little bit increases the maximum temperature from about let's say 55 to 65 degrees C. However, it ensures that the gradient between the center and the outer surface is a little bit lower. It's actually below 20 degrees C now, compared to the initial 34. Finally, this shows the impact of different cement types. So in case that we use cement type 2, which has a little bit lower heat of hydration. It's very efficient when very efficient solution if we want to achieve 2 points. We can reduce the maximum temperature in the element, and also we can decrease the gradient between the center and the surface. So this is very simple parametric study. And with this, I would like to conclude the presentation, and maybe I can show you something very quickly from the post-processor. So in here, this is the already calculated model in ATENA Studio Post-Processor. I would like to bring your attention to these results, because it shows the development of the degree of hydration over the structure, and actually it's not very clear from the where to find this parameter in the results. So it's actually hidden here. If you say the output value T alpha pairs and the item V2, it corresponds to the degree of hydration in the element. Now we can see the whole view. And for example, if I'm interested in looking in more details, how it looks inside, I can create a clipping plane. I think the thickness is about 8 meters, so in the middle it will be 4 meters. I can specify the 3 points for the clipping plane in here. I can apply it, and now I can see the distribution inside. If I don't want to see this mesh on the clipping plane, I can just specify it here. So this is it. This is after 28 days. If I want to see, for example, the degree of hydration at the peak temperature, it would be at step 26. We can see that at this step 26, which corresponds to the time of a little bit more than 4 days, we have the highest temperature inside of the structure, and the degree of hydration in the center is about 70%. Similar thing can be done for the temperature, where you can get the temperature distribution in the structure if you go to current C values and select the temperature item. And as I mentioned, for example, the humidity was kept constant at 1 for the whole analysis, so we can even review it here. So I guess this is it from for the example, and I see that there are some questions in the chat box. So so in the few minutes I would like to answer them. So Herman Kyong asks, can we use this software to model the water cooling pipe? Yes, we can do that. We even have when you install ATENA, there are some examples of the calculation, and one of them deals with the water pipe cooling. It's easy to simulate that because you basically define some elements within the structure which would represent the cooling pipe. You define their fixed temperature, and then this can be simulated. I'm not sure. Maybe is even shown in ATENA Center. If I go to tutorials and okay, so it's maybe it's not here. Transport and can. Okay, so no, it's actually this example. If you can now show my, if you can see my screen, it's this is a massive concrete segment, and in here we simulated the pipes for which we prescribed a fixed temperature, and they are providing the cooling for this massive concrete element during its hydration. So this example is even included in the installation. You can open it directly from the tutorial section. This is the model. So another question: are you able to model the internal stress due to the different temperature gradient? Yes, maybe I should have mentioned this one at the beginning. Today we were dealing only with the transport problem, but often this is done to get the temperature or the transport data, which can be later imported into the static module where we can simulate the cracking. So after the calculation, actually you get this kind of file, which is called thermal results, which is then specified in the static module, and the temperature is imported into the static module, and based on that we simulate the thermal expansion of the material and potential cracking. Can ATENA be used to calculate early age cracking while taking into account user-defined concrete creep and shrinkage values? Yes, maybe again this aims to the same question, to the same problem. Maybe we plan to make another webinar dealing with this in the future, where I will be showing specifically this one, because in ATENA you can define your own material model, which specifies how the concrete mechanical properties improve over the time thanks to the hydration. So we can simulate that at each step the concrete has different strength, different fracture energy, different tensile strength, etc. And then for this model we import the temperature data and simulate the cracking. Also, we can apply initial strain and simulate shrinkage. So all this can be included in such an analysis. So this was this question, and Bogdan Hedges, sorry for mispronouncing the name, asked how to choose the mesh size for hydration problems. I think for the transport analysis, I think the mesh sensitivity is not such a big problem. We should just be careful that there are enough elements to like for example per thickness or per the cooling thickness. However, this as far as I know, the temperature gradient should be linear, so it's quite well described with the linear elements. So I think we don't need to assume very small elements for the transport problem. Another question is: should we model the volume of insulation in a temperature problem, or in order to set it heat capacity or density? Yeah, as I mentioned, there are two options generally. once, if you have the insulation, you directly simulate it. You create some additional. So let me assume this model. It would mean that I would duplicate this surface and create an extra volume on the side, which would represent the layer of thermal insulation, and then I can have this directly in the model. Another method which I describe is that I already include this parameter to the heat transfer coefficient at the boundary, and this technically means that I use the lower heat transfer coefficient, and then the transfer between the external environment and the material is lower and simulating the insulation layer. Another question: can we model several layers of insulation with different removal time? Yes. Again, this can be done. Or maybe I should directly show the formula. So the total heat convection. Maybe I use different terminology before, but this is all included in the heat convection coefficient in this, and it's calculated as a sum of as an inverse of a sum of different layers. So this is the thermal insulation factor for different layers. This represents the small air layer at the surface. This represents the layer of the thermal insulation, and I can add several more layers. And as I run the simulation and define different intervals, I can change this coefficient and thus simulating the removal or addition of the insulation layers. And maybe the last question: is it possible to simulate or the removal of the formwork after, for example, 7 days? Yes. Again, then we just remove this factor and just use the convection factor to the external environment. And the early age cracking results in directly the crack's width or risk of cracking based on tensile stress. Yeah, the results would be directly the crack width, because ATENA is non-linear software, so we can simulating the cracking and then getting the crack width. As we see in a normal static analysis or cyclic loading in here, or beam underbending shown in here, these are directly the cracks, and we can get the crack width, and similar results can be obtained for the early age material. So I hope this was at least a little bit useful, a little bit understandable. And if you have any questions, please don't hesitate to contact us. You can reach us on our Czervenka hotline support. I'm typing the email address to the chat box right now, so do not hesitate to send us your questions or contact us in any other matter. And I hope to meet you soon at another webinar. So have a good rest of the day. Thank you for joining, and goodbye.
ATENA program produced by Czervenka company. You can find us via the website and download the program from it, or on YouTube by name Chervenka Consulting or in Facebook by name ATENA. Finally, we thank you for your attention, and for any inquiries, please don't hesitate to contact us. Have a nice day. Bye bye.